For this lesson, we are going to start getting into the different types of gases that we commonly find in your gas heat appliances. It could be for your water heaters, your stoves, and obviously your natural gas furnaces. So we're going to go over the different properties of these gases, what they're actually made up of, and some of the general characteristics of these types of gases. So the first thing that we need to know and understand is that all gases used to supply heat are called a fuel gas. The major component or part of these fuels is what we consider and call hydrocarbons. Now, hydrocarbons are made up of two different compounds. They're made up of hydrogen and carbon, hydrocarbon. Okay, so what are we doing with these compounds? Well, a lot of our composition of these different gases is really determined by the number of hydrogen and carbon atoms that actually make up these different gases. The more atoms that we have in these gases, the hotter they burn. Okay? For example, here, methane. Methane makes up pretty much the largest portion of natural gas, is methane. Methane has 4 hydrogen atoms and 1 carbon atom. Okay, so the chemical name for methane is CH4. 1 carbon atom to 4 hydrogen atoms. So when we are burning a natural gas furnace or a natural gas water heater, there's very little carbon that's actually in that compound, which is why it's said that natural gas burns cleaner than any other fuel gas that's out there. It burns cleaner than oil because oil has a lot more carbon than natural gas. Then we have ethane. Ethane has 2 carbon atoms to 6 hydrogen atoms. It's a heavier gas. The heavier the gas, the higher the burn. The dirtier the burn. Okay, so now that to understand combustion and to get things to burn correctly, we know that you have to have the combustion triangle. You got to have your heat, you got to have air, and you got to have a fuel. Well, in any of our gas-fired equipment, we have to have an ignition source, whether that's going to be a hot surface igniter, that's going to be a spark, that's going to be a standing pilot, whatever. Our fuel is going to be whatever it is that we're dealing with. The only thing that we can honestly control out of that entire combustion triangle is the amount of air that is being delivered to that fuel so that we can burn it efficiently. Propane. Propane is the next one. Propane has 3 carbon atoms to 8 hydrogen atoms. So even propane is an even heavier gas versus methane and ethane. It's heavier. So what is going to happen with these gases if we have a leak? Methane is very, very light, right? It's only got 1 carbon atom to 4 hydrogen atoms. It's a light gas. There's nothing to it, right? So if we have a natural gas leak in a home, we're going to naturally smell it because the fumes of that gas is going to rise. It's going to rise up into the air. Ethane, propane, they're heavier. They may not necessarily just rise up into the air. They'll sink. They'll sink to the floor because they're heavy. Look at butane here. Butane, that's a heavy gas. You got 4 carbon atoms to 10 hydrogen atoms. If there was a butane leak, it's going to pool to the ground. It's going to settle down on the floor, and then as it pools up, it's going to rise steadily up, 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 to eventually maybe where you'll actually smell it. Okay, so carbon and hydrogen atoms, the number of carbon and hydrogen atoms in each one of those fuel gases affects the nature of the gas. The more atoms in the compound, it's going to make it heavier than air. Your larger numbers of hydrogen and carbon atoms in the fuel, the more heat is going to be released. The burn is going to be hotter. The ignition temperature is going to be higher for each one of those different types of gases. Some additional characteristics of your fuel gas, such as how easy it can be controlled, how easily it's to control the flame, depends on the number of carbon and hydrogen atoms. So when we are thinking about a natural gas furnace versus maybe a propane heater, I have to be able to regulate a certain amount of gas to my burner so that I don't create an undue explosion because I'm just introducing way too much gas to air and spark ratio. I have to be able to control that. The only way I'm able to control that is through my gas pressure and through the orifices of that appliance. My gas orifices are just, they're metering devices. They regulate a certain amount of gas to each one of my burners. If those are not correct, I'm either introducing too much gas or too little. And that can honestly create a problem. The common fuel gases are not simply one kind of hydrocarbon, but they can be a mixture of many other gases. Okay, the fuel gases seen in HVAC industry may also contain other gases such as carbon dioxide, nitrogen, and what we call free hydrogen. Okay, they are not pure. They're not like 100% just carbon and hydrogen. They do have some other gases that are intermingled in there. Okay? Natural gas is pretty much an organic gas. It comes from your dead and dying plants, from the ground. Okay? Natural gas is a byproduct of oil. As oil gives off and decomposes and so on and so forth, it turns into natural gas. One thing that you should notice when you get into the HVAC industry is you watch the prices of oil and natural gas. And you'll see that as the price of oil goes down, so will the price of natural gas. As the price of oil goes up, so will the price of natural gas. They are literally the two same products that we find in the earth. People will disagree with it and people will say different things, but they are pretty much almost the exact same compound. They come pretty much from the same exact thing, dead and dying plants. Okay? So they're going to be usually found. Your natural gas pockets are going to be found pretty much where oil is present as well. Okay? Natural gas pockets are going to sit above where that oil is. If they dig down just a little bit more, they're probably going to hit the oil. Okay, some natural gas from garbage and cow manure is now being used, believe it or not. Okay, liquefied petroleum, or better known as LP gas. That can be propane or butane or a mixture of the two. Okay, LP gases are transported and stored in tanks. LP gases are usually used in areas where gas lines are not available. Okay, so when you're driving around and you're looking at neighborhoods, take a look. If you see big white cylinders on the side of the house, those are propane cylinders. That house is being heated by propane or butane. If you look on the side of the house and you see a meter, that's a natural gas meter. That's metering the gas that's coming into that home. LPG is stored under pressure. So much of the gas is in a liquid form inside those types of tanks. So as the fuel is drawn from the tank, it turns to a gas and then is burned in the same way as every other gas. Okay? Your propane grills outside, those cylinders are filled with LP. Propane, it's a liquid. But when you open up that valve, that liquid begins to change to a vapor. It is that vapor that you are burning when you turn on your propane grill. The same thing applies to your propane-fired water heaters, your propane-fired gas furnaces. Okay? However, one thing that we have to understand is that when natural gas comes out of the ground, it's odorless. There's no odor to it. There's no color. So what makes natural gas smell? Those that have smelt natural gas knows that it kind of has like a rotten egg smell to it. Well, that rotten egg that you are smelling is actually sulfur. When it comes out of the ground and it goes through its process of being delivered to homes, the gas company puts and introduces sulfur into that gas so that it is made easily detectable in the event of a leak. Okay? That's why we have it. Another concept that we have to think about is the specific gravity of a gas. Okay, the specific gravity is the weight of a substance compared with the same volume of another substance. Okay, fresh water is used as the reference substance for liquids and solids. Okay, so if the specific gravity of a liquid, so for example, is 2, it is twice the weight of the same amount of water. The specific gravity of water is 1, just so that everybody understands that. Okay, so for gases, air is used as the reference for a lot of our substances. Okay, specific gravity of a gas is calculated by weighing 1 cubic foot of gas and comparing it to 1 cubic foot of air. So both the air and the gas must be at the same temperature and pressure when that comparison is actually being made. The amount of gas is given in a given volume will change or vary with pressure. The pressure will vary with temperature as gases expand and contract with temperature and change. Again, back to a same concept. The higher the temperature, the higher the pressure. So if a propane cylinder is sitting out in a hot sun, the pressure inside that cylinder is going to rise. And when that pressure rises, I have more pressure inside the gas line, which is why propane cylinders have relief valves on them. Those relief valves are meant to open in the event that the pressure inside the cylinder gets too high. It's going to release some of that pressure. Every once in a while, maybe in the dead of summer, For people that have propane tanks, you may every once in a while smell a little bit of propane coming out. That's normal. That's those relief valves working. That's actually a good thing. Okay? So the specific gravity is going to change on our gases depending on that temperature change. It's either going to expand or contract. The specific gravity of air is 1 as it is used for the reference material. A lot of our specific gravity when it comes to our gases is going to be measured at a standard temperature of 69.8 degrees. But we can simply round that up to 70 degrees. Okay? Our gases are measured at 70 degrees and at an atmospheric pressure of 29.92 inches of mercury. Those are the standards that we use when we are dealing with the chemical composition and specific gravity of gas. Okay, so the specific gravity of gas is going to be anywhere between 0.4 and 0.8 versus air has a specific gravity of 1. So since natural gas has a lighter specific gravity, it's going to rise up into the air, which is why natural gas is so easily detectable when you have a natural gas leak, because you smell that sulfur. It's going to rise up. Now, propane has a specific gravity of 1.5. It's heavier. Remember, the specific gravity of air is 1. So it's heavier. So if I have a propane leak, it's not going to rise up. It's going to settle towards the floor or towards the ground. Okay, butane has a specific gravity of 2. So it's a much heavier gas. So if I have a butane leak, it's going to land more towards the ground or towards the floor. Okay? If these gases are released into the air, they will fall instead of rise, and they will not mix readily with the air. Okay, butane and propane will drift into a lot of your low spots, or it's going to pool, creating an explosive environment if open flames or spark is present. Now, I've seen a couple of instances with propane leaks and have seen some of the damage that can happen with pooling of propane because of the failure to find propane leaks or failure to even check for any sort of leaks. As a HVAC mechanic, it is actually very good practice to spray all of your gas fittings and gas piping with some soap bubbles on all of your joints to see if there is any sort of leaks. If there is, it's going to bubble up on you and you're going to see it. Because if you don't do something like that and there is a leak and there is a pooling going on, you may not necessarily know it until it's too late. I've seen a couple of instances where there's been a pooling of propane and either someone plugged in a hair dryer or a vacuum or whatever, and there was a little bit of static electricity, and there was enough concentration of that gas inside the house. It created an explosion and, pretty much leveled buildings. So it is a dangerous thing, but we do have that knowledge and that technology to at least locate these leaks. If you are installing your natural gas lines or propane lines, by code, you have to pressure test those lines with nitrogen, and you have to leave it for about 24 hours just to make sure that there are no leaks. If you fail to do something like that and there is a leak, you're the one that's going to obviously hang for it. But you do have to take those precautions to make sure that you are not creating some sort of explosive environment. So it's important to know the effects of flow of gas through orifices, especially knowing the specific gravity. Because remember, specific gravity is basically the weight of that gas. So why do we need to know it? It's important. You got to know how that gas is going to flow through our pipes, through our orifices, and how it's going to affect your burners in your equipment. Remember, we have, in our gas lines, we're going to have gas regulators. We're going to have gas orifices. All of those components are going to control the amount of gas to your appliances. Okay? Like the gas orifice is nothing more than a small hole in a fitting that we call a spud. And that is used to limit the amount of gas flow to your burners. Your flow in the specific gravity of that gas is going to determine how much gas is going to be delivered to your burners. So that's why it's important to understand and know your specific values. Okay, heating values of all of your gases. Well, heat energy produced when burning a fuel is commonly expressed in BTUs, or British thermal units. Okay, 1 BTU will raise the temperature of 1 pound of fresh water 1 degree. That is the definition of a BTU. A BTU will raise the temperature of 1 pound of water 1 degree. Okay, burning an ordinary wood match produces approximately 1 BTU of heat. So light a match, put your hand over that match, and feel the heat that's coming off of it. That's approximately 1 BTU. Okay? Again, 1 pound of water at 7 degrees plus 1 BTU will raise it to 71 degrees. Okay, so for example, we need to heat 10 pounds of water to 100 degrees. That's going to require 1,000 BTUs of heat. Okay, the heating value of gas is the amount of heat released when 1 cubic foot of gas is completely burned. Natural gas, primarily again, is methane, has a heating value of about 950 to about 1,150 BTUs per cubic foot. In a lot of our gas sizing calculations and BTU calculations, we pretty much round our heating value of natural gas to 1,000. That's pretty much the standard for a lot of stuff. It's just simply because of the sake of math and calculations. So anytime we use a heating value for methane, we use 1,000. Propane has a heating value of about 2,500 BTUs per cubic foot. Butane has a heating value of about 3,000 BTUs per cubic foot. Another term that we usually use in this industry is called the THERM. A THERM is equal to 100,000 BTUs of heat energy. So if you're working on a natural gas furnace or a natural gas boiler or something like that, and it has an output value of 200,000 BTUs, we usually say that it has a BTU value of 2 therms. It's just another term that's out there, but that's where we come up with that term. Okay, a therm of natural gas is 100 cubic feet of gas. And visually how we figure that out, we take 100,000 divided by 1,000, it comes up with 100. 40 cubic feet of propane contains a therm of heat energy. The way we figure that out, we have 100,000 divided by 2,500 BTUs, and that's going to equal 40. Hourly use of gas, well, input rates are the measurement of the hourly use of gas in an appliance. When you look at a nameplate on a piece of equipment, you're going to see that it has an input rate. Okay, that input rate will be in cubic feet per hour. Your input rate can be converted to and from BTUs per hour. To do that calculation, you have to take your heating value of your gas per cubic foot and times it by the gas flow rate in cubic feet per hour. If you want to figure out your gas flow rate in cubic feet per hour, you have to take the input rate, which is going to be stamped in BTUs per hour, and divide it by the heating value of that gas in BTUs per cubic foot. So for example, if we have a natural gas water heater and it needs 35,000 BTUs per hour, so we're going to find that required gas flow. So if we take 35,000 BTUs per hour, which is what we need, and we know that natural gas has 1,000 BTUs per cubic foot, we take 35,000 divided by 1,000, and we're going to need 35 cubic feet per hour of gas to flow to that unit in order for it to burn at 35,000. Input rates are important for a lot of reasons, and again, especially for your gas pipe sizing for all of your appliances and furnaces. If we do not size or deliver the correct amount of BTUs to that furnace, we're not going to be able to achieve the correct burn, and we're not going to be able to get anything to burn efficiently like we should. I will be covering how to do gas pipe sizing in a later lesson, but for the main point, what you need to understand is how some of these things are calculated and where things are coming from.